This is a moments question. For part 1, we're solving a simple scenario with two symmetrically placed supports on a uniform ruler, and we're trying to work out the reading on one of these force meters. For part 2, we're thinking about whether or not these forces form a couple. Part 3, we have an unknown mass placed at an unknown distance from A. We're trying to work out what is the weight and what is this distance by taking moments. And then finally, for part 4, we have an explanation question. We're thinking about whether the ruler, being at an angle, will affect our moments. So we'll be discussing this diagram here. Okay, so for part 1, a student investigates moments by suspending a 100 centimeter ruler from two force meters, A and B. A and B are attached to the ruler 12 centimeters from each end, and then we're given that in our diagram as well. Their supports are adjusted to make A and B vertical and the ruler horizontal. We're told the ruler is uniform and weighs 1.12 newtons, and we're trying to determine the reading on A. So I've just drawn on the weight force as well as two distances, 38 centimeters from A and B. This is a uniform ruler, so the weight acts directly in the middle. The whole thing is 100 centimeters long, which is how I ended up with the two distances that I worked out. In a scenario like this, where the supports are symmetrically placed on a uniform ruler, the forces that they exert on the ruler will be equal. So our answer would just be half of 1.12. So 1.12 divided by 2, which would just be 0.56. And that should make sense if you think of this intuitively. If you have a ruler where the overall weight is in the center, and then you have two supports which are equidistant from where that weight force acts, they should provide the same upwards force to counteract that downwards weight force. For 5.2, the student suggests that the forces exerted on the ruler by A and B act as a couple, and we want to discuss whether or not his suggestion is correct. So what is a couple, first of all? A couple is when you have two forces that are equal and opposite that don't act through the same point. So an example of that could be if you have some kind of rod, we have on one end, we have a force of, let's say, 10 newtons. On the other end, we have an upwards force also of 10 newtons. The two forces are equal and opposite. One goes up, one goes down. They're both 10 newtons, and they don't act through the same point. They are acting along different lines. The 10 newton force on the left acts through this line, this force acts through this line. So in our scenario, we have two forces, both 0.56. So here is one force which is 0.56. Here is the other. The two forces are equal. They act at different points, so they don't act through the same point, but they're not opposite. And if they're not opposite, they wouldn't form a couple. So for 5.3 we have the student hangs a mass of weight W on the ruler between A and B, as shown in figure 9. He adjusts the supports so that A and B are again vertical and the ruler is horizontal. The mass hangs at a distance of D from A. We're also told that the reading on A is 0.82 newtons and the reading on B is 0.62 newtons. And then we're trying to determine W and D. Okay, so let's draw our forces on this diagram. So we know what the forces at A and B are. We have the force at A is 0.82 newtons, and the force at B is 0.62. There is a force downwards here of W, and then we also have the weight of the ruler, which acts in the middle and has a value of 1.12 newtons, same as the weight of the ruler from earlier. The weight is in the middle, so this distance here would be 38 centimeters. And this distance here would be the same. Okay, so now we can start to do some calculations. So the first thing that we can do in this scenario is say all of the upwards forces equal the downwards forces. So we can say that 0.82 plus 0.62, those are the two upwards forces, would be equal to W plus the other downwards force of 1.12. Rearrange for W, and we end up with 0.32. So let's just put that on our diagram. So this will be 0.32. So in these kinds of questions, we can form two sets of equations. One is equating upwards forces and downwards forces, which is what we've already done. And the other would be a moments equation. Sometimes you have scenarios where you also have horizontal forces. So you can do vertical forces all equal, so upwards forces equal downward forces. You can do horizontal forces equal, so forces towards the right equal forces towards the left. And then your third equation would be the moments equation. In this case, there are no horizontal forces, so we just have the vertical forces equation. That's given us 0.32 newtons, so the weight of W. Now we can do our moments equation. So because we're trying to work out the distance d, I will take moments about this point over here, because the distance from that point to W is d. It makes things a little bit easier. Let's then identify what are our clockwise moments and anti-clockwise moments. So if we're taking our pivot point, so the point that we're taking moments about, to be here, the force of 0.32, if we start where the force acts, follow it along, and go around the pivot, that will be a clockwise moment. This would also be a clockwise moment. Starting at the base of this force and going around, that would be an anti-clockwise moment. Okay, so then what we do is we set clockwise moments equal to anti-clockwise moments. Moment is force times perpendicular distance. So we'll start with the 0.32. 0.32 times the perpendicular distance, which is d. So that is this distance times this force, plus this distance times this force. So that will be 1.12 multiplied by 0.38. Those are our clockwise moments added up. This is equal to our anti-clockwise moment, which would be 0.76 multiplied by 0.62. And now we can solve this equation for d. We can rearrange and solve for d. So 0.32d would be equal to 0.62 times 0.76 minus 1.12 times 0.38. Bring the 0.32 to the other side. I'll work out what the right hand side is in my calculator. That will be 0.0456 all over 0.32, which gives us 0.1425. So W is 0.32, and then D is 0.14 meters. 5.4. A second student sets up the same apparatus as shown in figure 9. She suspends the mass in the same position on the ruler as in question 5.3. So question 5.3 was this one. The weight is in the same position as before. She moves the supports to make A and B vertical, but does not make the ruler horizontal. Discuss whether the readings on A and B taken by the student are different to those in 5.3. Okay, so I've drawn a diagram below which represents the scenario. We have our ruler is at an angle. The forces are still vertical, so the two support forces, which I've called TA and TB, are still vertical. The distances between the forces are all still exactly the same. So this is still 0.14, this is still 0.38, same as before. The two downward forces are the same as well. So we want to now think about how, if at all, have TA and TB changed and why. So let's start with a moments equation. So this is an explanation question, so we won't actually have to do any calculations for this, but to explain it, I think getting the equation will make things much clearer. Whenever we're working out moments, we have to do force multiplied by perpendicular distance. So if again, we're considering this to be point A, this to be point B, if we take moments about point A, same as before, To work out the moment of the 0.32 Newton force, we have to do that force multiplied by the perpendicular distance. The perpendicular distance would be this length here. So we consider this triangle where the hypotenuse is 0.14. The angle would be the same as this angle here. Those two are corresponding angles. So if I were to draw a quick triangle of what we have there, we have this is 0.14, this is theta, this is 90. This length will then end up being 0.14 cos theta. And it's a similar kind of thing for the rest of the distances too. So if I wanted to work out the perpendicular distance from A to the 1.12 Newton force, again I would just do this distance multiplied by cos theta, and that will give me this distance here. It's the exact same kind of calculation. So then our moments equation will end up being 0.32, that's the weight that was attached to the rod, multiplied by its perpendicular distance, which was 0.14 cos theta. Again, that is this distance here. And then we add on the other clockwise moment, which would be 1.12 multiplied by its perpendicular distance, 0.38 times cos theta. And finally, this is equal to the anti-clockwise moment, which will be the horizontal component of this distance. That distance was 0.76, so it'll be 0.76 cos theta. So TB multiplied by 0.76 cos theta. Now notice how all of these terms have cos theta within them. Therefore, we can just divide the whole thing through by cos theta. We end up with 0.32 times 0.14 plus 1.12 times 0.38 is equal to TB times 0.76. Now that moment's equation is identical to what we would have if the rod were horizontal. Notice how this 0.14 is this distance here, the 0.38 is this distance here, and the 0.76 is this distance here. So if our rod were horizontal, all of these distances would be the same distances that we would use when setting up our moments equation. For that reason, our force of TB would be no different when the ruler is at an angle, as we see here, versus when the ruler is horizontal. So there will be no change in TB. The downward forces haven't changed. If TB hasn't changed, well then TA mustn't change as well, because TA plus TB must equal those two downwards forces. So there will be no change overall. So how would we say this for, how many marks is it? For 2 marks. So all we need to say is that the forces do not change, as all of the distances are multiplied by the same factor of cos theta. The cos thetas then cancel out when doing our moments calculation, and that should be enough for those 2 marks.